Hello everyone, I'm Taylor Rosen from Penn State University in the Department of Geosciences. This is my final update for the Texas A&M Summer 2020 O-REU. I'm studying the effects of temperature-dependent coefficient of thermal expansion on thermal stress weathering in small asteroids. I worked under faculty mentor Dr. Justin Wilkerson with graduate student mentor Joshua Vancura. I'd also like to thank my other sponsors and collaborators. First, I'd like to talk about thermal cracking. Cracking is caused by stresses. Thermal cracking stems from thermal stresses, or stresses caused by a change in material temperature. These thermal stresses can be residual, meaning they're present even after the source of stress is taken away. And over time, these residual stresses can crack surfaces. I'm sure many of you have seen this develop over time, seeing sidewalk cracks lengthen during the hotter months. Thermal cracking and even failure can also happen much faster with rapid temperature change. Like taking glass from an extremely hot furnace or heat source and cooling it quickly can cause a lot of internal stresses to develop. And doing this repeatedly or cyclically can accelerate material breakdown. This process is deemed thermal cycling, as you'll see in this clip. Different materials also have unique coefficients of thermal expansion, or CTEs. The CTE is the relative ratio of the change in length to the change in temperature. Traditionally, these are thought of as being spatially the same through a piece of material and monotonic with regards to temperature. Monotonic meaning it either will only increase or decrease with changing temperature. It won't do both. But as you can see to the right, a graph representative of the CTE in the asteroids I'm studying, this is not the case. As we see the CTE decreasing, then increasing with increasing temperature. CTE variation can also induce thermal stresses. As you see to the left, we solve this compatibility equation to see how thermal stresses arise. The thermal stress should be zero for a constant and linear temperature fields if the CTE is also spatially constant. But in my case, the alpha value is changing, or the CTE. Thus, microscopic stresses will develop. On this slide, I want to show you all how material deformation occurs under different temperature fields. On the left, under a constant temperature field, as you can see, other than the middle of the specimen, which is being deformed and broken due to applied tensile stresses, red being relatively high stress, blue being low, the dark blue portions grains are not subject to any sort of distortion or deformation. Whereas in the middle, this material underwent a linearly decreasing temperature field from high to low. This middle material is a fiber embedded in a bulk matrix, and as you can see at material boundaries, such as the circular fiber intrusion at the end of the bulk, moderate to high stresses are experienced. On the right, there is a slab of material exposed to a nonlinear temperature field. As you can see upon quick heating and cooling, the material quickly bowed, and an imbalanced temperature profile from inside to outside the material developed. It's mimicked by a similarly shaped stress field, and tension is at the surface, and that can cause crack propagation and failure. This nonlinear scenario is what I'd like to focus on. Widening the scope to look at asteroids, I'd like to examine trends in their surface temperature fields. As you can see in Figure 5, their temperature fields are nonlinear. They change significantly with changing distance from the Sun. This distance is measured in AUs, which is roughly 1.50 times 10 to the 11th meters. And these two lines represent chondrites, or stony meteorites. A carbonaceous chondrite is a much rarer type of chondrite, but for the purposes of this presentation, I'll be focusing on ordinary chondrites, or the red line. Now, I'd like to touch on how my group modeled asteroid temperature fields. I'd like to first develop a point of reference in what we're studying. In this project, we're studying inclusions on the order of centimeters, stemming from asteroids no more than a kilometer in diameter, and roughly 1 AUs from Earth. Over to the right, here you can see a schematic of how we consider a centimeter-sized sample. This encapsulating circle represents a spherical rock of diameter d on the order of roughly 10 centimeters from a chondrite that has spherical metallic inclusions represented in green, of radius r sub I. At any macroscopic location zeta, a microscopic coordinate y could be surmised, and this factor of 2L represents separation, with L being nearest neighbor distance. Heat transfer between these green inclusions is modeled as thermal conduction, the transfer of energy through microscopic particle collision. It's also worth noting that a fast temperature change in the bulk rock can make a nonlinear temperature change through space, between these green inclusions. My group's model focuses on analyzing thermal stresses in these spherical rocks. Here, I have a flowchart of the thermal stress model that my group implemented in MATLAB. As you can see here, we have another zero stress compatibility equation, very similar to the previous, with strain substituted as the non-gradient term inside the parentheses. As you can see here in the flowchart, we go all the way from steady state temperatures and thermal expansion, branching off into strains, and eventually macroscopic and microscopic thermal stresses. My research focused on the macroscopic thermal stresses, i.e. the stress affecting the surface of the spherical rock, from figure 9. As I move into discussing the results of my research, I'd like to discuss the primary modification I did to the project's existing code. The code previously calculated macroscopic stress with a constant CTE, but as seen earlier, the CTE was non-monotonic with temperature. I modified the macroscopic stress calculation to include this dynamic CTE as it varied with depth in the calculation. Seen below is a comparison between the rotational period of the existing asteroids and their lifetime in years. Figure 10 was before the dynamic CTE implementation. Figure 11 was afterwards. The first thing that I noticed was the rock's lifetimes are 3 orders of magnitude shorter after implementing the dynamic CTE, pointing to much higher stress magnitudes. Also, as seen with this red line, this linear relationship between period and lifetime is preserved, even with the 3 order of magnitude shorter lifetime. And as expected, Figure 11's linear region slope increased compared to Figure 10's linear region due to a much shorter lifespan. Here I'd like to emphasize the effect of this dynamic CTE on the stress calculations in these asteroids. As seen here on Figure 12, the orange curve represents the max macroscopic surface stress before the dynamic CTE implementation. The blue curve is the stress with the CTE implementation. As you can see, the dynamic CTE's max stress curve is 10 to 20 times higher than the constant case, and both curves have a period sweet spot of sorts. The relative maximum occurs between 1 and 10 hours. I'd also like to point out, going from the 17th to 18th data point, the spike in max surface stress on the blue curve. I believe this jump was due to a point of inflection from the CTE graph with the temperatures involved, shifting from 230s to 240s Kelvin and higher, as you can see below. Here in Figure 13, I've graphed the maximum and minimum surface stresses for the dynamic CTE, and the same curves for the constant CTE case plotted versus rotation rate. The dynamic CTE stresses understandably vary far more, since the CTE varies as well, but the magnitude of the surface stresses are 1 to 2 magnitudes greater in the dynamic case, with the max and min peaks being roughly 2 orders difference. With regards to the max surface stresses, we saw this relationship last slide, but it's worth noting the min stresses also follow this pattern too. And it makes sense that the largest stress magnitudes are occurring at an intermediate rotation rate. If the asteroid is spinning very slow, at any given section, the thermal fields over a given section become homogeneous. As you see the stress values in the dynamic case being nearly constant for the first 3 data points, and with the constant case as well. On the flip side, spinning very fast creates a near isothermal environment, as I stated earlier. After looking at all this data, I think it begs asking, what is the significance of this research? I believe this significance comes into play for learning how our near-Earth objects evolve. With this thermal stress model, asteroid breakdown can take 20 years instead of 20 million years as previously thought. Prior to the recent research regarding asteroid breakdown, popular scientific theory deemed the main mode as collisions with very small pieces of debris. But as we've seen today, thermal stresses are a grand presence, especially closing that gap from 20 million to 20. Looking at this fragility further with my CTE implementation, these events of thermal cycling and stress exposure are very sensitive, as you saw how stresses can vary significantly with small changes in temperature. Ultimately, I believe this brings into account the idea of a sweet spot, or Goldilocks zone, circled in figures 14 and 15, possible areas for terrestrial objects to survive and even hold liquid water. The various objects marked in white within the circle are nearly all asteroids. I plan to recreate figure 15 for the dynamic CTE case in the future. I hope this presentation brought you a deeper picture of how mechanically dynamic our environment near Earth truly is, and the importance of understanding it through a thermal scope. Thank you for your time.